Hello, in this video I'm going to talk about derived rules. So, let's remember this fact about theorems, that every instance of a theorem is itself a theorem. And what this means is that if you have a theorem and you have an instance of the theorem, then that instance can be derived inside of any derivation whatsoever, because we can copy the derivation. Now, copying the derivation of the theorem is tedious, though. So once we've done a derivation of the theorem, we know that we could stick it inside of any other derivation. So once we derive a theorem once, after that we can just put in any instance of the theorem we like, and then as a justification, we write down the theorem number. So each of our theorems gets numbered, and then we think, oh, well, I did a derivation of this theorem, and I want to stick it an instance of this theorem in this other derivation I'm doing for my homework. I can write down the theorem instance, and then instead of having to do the whole derivation, I'll just write down the theorem number. So that's kind of handy. Here's one important theorem that I'm going to be coming back to repeatedly. It's called De Morgan's. It's this. It says, suppose it's a biconditional. The left side is not P or Q. The right side is not P and not Q. And it says either it's the case that both not P and not Q, and also it's not the case that P or Q. Either those are both true or they're both false. The negation of the disjunction and the conjunction of the negations, those always agree, both true or both false. And that's theorem 66. It's problem 2066. There are a couple of versions of these theorems that have to do with the way in which negation and disjunction and conjunction interact. They were first sort of explicitly recognized by somebody named De Morgan, and that's why they're called De Morgans. And this is one version of them. It's the most useful version, as we'll see subsequently. So, how might we use De Morgans when we're in a derivation? Well, it might be because we have not P or Q, which we can't do much with, but we could turn that into not P and not Q, which would be useful. So how would that go? Well, suppose we have not P or Q. Well, like, oh look, I've already derived this problem 266, which is theorem 66, so I'm going to write it out here. So I just write out the sentence, and my justification is T66, because I'm saying, look, I could write the justification for the whole theorem, but it's over there, and if you copied it here, it would work. Let's not waste time. Let's just put in the theorem. It's the theorem and not the whole derivation. And then we could apply BC, and we'd have, if it's not the case that P or Q, then it's not the case that P and it's not the case that Q. And now with 5 and 7, we can do modus ponens, and we get not P and not Q. And while 5 is not very useful, you could use it in an indirect derivation for boxing and canceling, but that's about it. 8 is quite useful because 8 you can apply simplification to, and you can get not P from it and not Q from it. So 8 is better than 5. So this is nice. You could use the theorem and then take a couple of steps to get to the theorem, but you can do something better than that. We can make a new rule, which we'll call DM, and that will be short for De Morgan's. And the rule is going to compress into one step, putting in the theorem and then applying the inference rules. So what does it look like? Like this. We have not P or Q, and then we just jump to not P and not Q, and the justification is 5 DM. And we get to skip 6 and 7, and we have a simpler justification as well. So, so that's good. That's nice. Derived rules are useful because they can help us go through steps more quickly once we've derived them. Now, any derivation you can do with a derived rule, you can do without a derived rule. That's why they're okay to use, but they're helpful. So, if you want to enable derived rule, what do? Well, you find the associated theorem. And so to enable this version of De Morgan's that I've been showing you, you would do derivation 266. And you might think, well, what other derived rules are there? Which ones should I do? We'll be talking about those over the course of the next several modules. This is getting us used to them. So in the next video, I'm going to actually show you how to do derivation 266 because it's not easy. So you're going to want to follow along with that video, and I recommend that you do the derivation as I'm doing it, because then you'll have the rule derived, and I'm going to suggest that you actually use that rule a bunch. So next video, derivation 266.